This is a BocaPhysics introduction to analyzing the stability of linear and nonlinear differential equations. In today's lecture, I'm going to discuss the stability of solutions to linear and nonlinear differential equations. This topic should be covered in the second semester of differential equations. However, it's usually omitted in spite of the fact that it has wide use in areas such as ecological modeling, neural networks, the stability of plasmas, in particular the stability of fusion plasmas. And people look at things like the resistive tearing instability, and the list goes on and on. In order to illustrate these concepts, I'm going to be showing you some plots of certain kinds of systems. And those plots were generated using Python script, and I also made use of the great library Matplotlib. I've posted the Python script on the BocaPhysics website, so be sure and take a look at that. I'm going to begin with a very familiar system today, that of a pendulum, a simple pendulum, and a little bit later on we'll look at a damped pendulum. We'll also look at just a bunch of math problems, just to look at the different kinds of stability that can arise. So, using the pendulum, has length L, and is displaced from the vertical by an angle theta. The differential equation that describes this motion is equal to the second derivative of theta with respect to time, plus g over L sine theta is equal to 0. And L, of course, is the length of the pendulum. G is the acceleration due to gravity. Typically, in a general physics class, you make the small angle assumption and replace sine theta by theta. And the solution here will be some linear combination of cosine and sine, and the coefficients to be determined are determined by the initial conditions. We are interested in stability, not just merely writing down a solution to the linearized form. So I'm going to take a little bit different approach. I'm going to introduce two parameters, first of which x is equal to theta, and y is equal to d theta by dt. You can rewrite this equation as dx by dt is equal to y, and dy by dt plus g over L sine x is equal to 0. So I've converted a single second order differential equation to two first order differential equations. And I'm going to go ahead and move this over to the right hand side. And these two equations form a certain kind of system called an autonomous system. The system is composed of two first-order differential equations. dx by dt is equal to some function of x and y, and dy by dt is equal to some function of x and y. In order that there be a unique solution, the functions f and g must be continuous, the partial derivatives must be continuous, and that unique solution is determined by the initial conditions. Look up here, clearly the functions themselves and their partial derivatives are also continuous. Okay, so let's go ahead and solve this system. First, before I solve that, let's go ahead and return to the linearized version. So we'll have dy by dt is equal to minus g over L times x. Well, x can be written as x is equal to some constant c times sine of square root of g over L times t minus s. Y can be written as some constant c times square root of g over L times cosine square root of g over L times t minus s. Now c and s are constants to be determined by the initial conditions. If I square both of these equations, and if I divide this term by g over L and add them up, to save myself some room, I'm not writing the arguments here, but basically you have c squared times sine squared plus c squared times cosine squared. That's just going to be c squared. This is the equation of the ellipse. So the trajectory in this case is going to be elliptical in shape. When you're investigating the stability of these trajectories, it's useful sketching out in a phase plane and the trajectory or orbit or path that a particle follows, if you can imagine a particle being governed by these equations, would look like this. Now, which way is this going? Is the particle going to be traveling in a clockwise or counterclockwise direction? Let's take the first quadrant here. In that first quadrant, x and y, of course, are both positive. If I look at my first differential equation, dx by dt is equal to y. So if y is positive, dx by dt is positive. So that means the particle is going to be moving to the right, and that is going to be clockwise direction. On the same hand, by the same token, I could have looked at dy by dt is equal to minus g over L times x. X is positive, that means dy by dt is negative, and that means the particle is going to be going downward. So again, in a clockwise direction. Now, this particular system is centered, and it's of interest, you know, what happens if f or g, or actually in particular, both of them are equal to 0? Well, suppose I divide dy by dt over dx by dt, that's dy by dx, and that's going to be equal to g over f. So in the case if g is equal to 0 but f is not, then you'd have just dy by dx is equal to 0. On the flip side, if you had f was equal to 0 at some particular point, but g was not, you could just invert this expression and you'd have f over g. And again, dx by dy would be equal to 0. But what if both f and g are equal to 0? What does that mean? Well, the only possible solutions then are for dx by dt and dy by dt to be constants. So essentially that is the equilibrium. So the point at which f and g are equal to 0 is called a critical point. And when you're investigating stability, you want to see how do these systems behave in the neighborhood of the critical point. For most of the systems that we're going to investigate, the critical point will just be at the origin, it'll just be at 0, 0, like it is in this case. However, once we revisit the pendulum problem, but not linearized, and if we looked at the damped pendulum problem, we'll look at some critical points that are not located at 0, 0, 0 at the origin. Okay? focused on linear and nonlinear autonomous systems. I can write my this equation out, breaking apart the linear terms and the nonlinear contribution. So we have dx by dt is equal to some constant a times x plus some constant b times y plus some nonlinear contribution. dy by dt can be written as some constant c times x plus some constant d times y plus some nonlinear contribution, and that should be g. It is a lot easier to deal with linear systems. As it turns out, a lot of the stability arguments that we're going to make and carry over from the linear to their nearly linear counterparts. I'm going to go ahead and treat the linear systems first. So this is a linear autonomous system. And it's the case that a times d minus b over c cannot be equal to 0. Looking at systems for which the critical point is 0, 0. We can, of course, look at critical points located in other areas of the phase plane, and in fact, we'll do that a little bit later on with when we revisit the pendulum problem and also the damp pendulum. But for now, we'll just look at systems where the critical point is at 0, 0. So you can see both of these terms would automatically be equal to 0. Solutions of these equations will have a form some constant times e to the RT plus some constant b times e to the RT as well. I'm going to substitute this in. One way that there is going to be a non-trivial solution here is that if the determinants of these coefficients vanish. So R is going to be a solution to this characteristic equation, and as we'll see by determining what kinds of solutions to get, in other words, are they positive, are they the same, are they negative, are they complex, are they purely imaginary, you'll be able to determine what kind of critical point the solution is going to have. Okay, so let's take a first, for instance, let's suppose that x is equal to a. Suppose that dx by dt is equal to minus 2x. And dy by dt is equal to minus 2y. We go ahead and plug this into the characteristic equation. Case, both of the roots are equal to minus 2, so they're both going to be real. They're both negative, and they have the same value. Two solutions are x is equal to x naught times e to the minus 2t, and y is equal to y naught times e to the minus 2t. Let's go ahead and plot those out on a phase plane to see what kind of a critical point 0, 0 is. A trajectory that starts at some point follows a straight line towards the critical point. This kind of critical point is called a proper node, and the system is asymptotically stable. For the system dx by dt is equal to 2x and dy by dt is equal to 2y, the roots of the characteristic equation are equal and positive. The critical point is still a proper node, however the straight lines emanate from the critical point rather than approaching it. Hence, this system is unstable. Okay, so let's look at the linear autonomous system. Dx by dt is equal to minus x, and dy by dt is equal to minus 2y. In this case, a is equal to minus 1, b is equal to 0, c is equal to 0, and d is equal to minus 3. This leads to the characteristic equation, r squared plus 4r plus 3 is equal to 0, and the roots, therefore, are going to be minus 1 and minus 3, which you could look at from inspection. So the roots are going to be real, they're negative, but they are different in this case. Solutions will look like this. X is equal to x naught e to the minus t, and y is equal to y naught times e to the minus 3t. The roots of the characteristic equation for this system are negative and different. A trajectory that starts anywhere other than on the y-axis will approach a critical point along the x-axis. A trajectory that starts on the y-axis will be a straight line. This kind of critical point is called an improper node, and this system is asymptotically stable. Next, I'm going to consider the linear autonomous system. Dx by dt is equal to minus 3x, dy by dt is equal to y. In this case, a is equal to minus 3, b and c are 0, and d is equal to 1. These coefficients in each of the characteristic equation, r squared plus 2r minus 3 is equal to 0, and solving for the roots, wind up with minus 3 and 1. Again, you can just do that by inspection. They're both real, one is positive, one is negative, and their point solutions are going to be x naught e to the minus 3t, and y is equal to y naught e to the t. So let's take a look at what the trajectories look like in the neighborhood of the critical point 0, 0. When the roots of the characteristic equation have opposite signs, the critical point will be a saddle point. The trajectories shown approach the critical point along the x-axis, but then bend towards the y-axis and go off to infinity. Only trajectories that are exactly on the x-axis will approach a critical point as t goes to infinity. Saddle points are unstable. We'll consider a slightly more complicated linear autonomous system. This time, the function g depends on both x and y, so we have dx by dt is equal to minus 2x, dy by dt is equal to x minus 2y. So a is equal to minus 2, b is equal to 0, c is equal to 1, and d is equal to minus 2. And this time, once again, both roots are going to be the same. They're both real, they're both negative. However, the solutions are going to be a bit different. X is still just going to have a single exponential term. It's going to be x naught times e to the minus 2t. Y, on the other hand, is going to be equal to y naught times e to the minus 2t plus x naught t e to the minus 2t. And there's your solution. This actually will once again lead to an improper node, but its form will look a little bit different from before. The critical point for this system is also an improper node because the roots of the characteristic equation are equal and real. This critical point is also asymptotically stable because the trajectories approach a critical point as time goes to infinity. This plot is different from the other improper node plot because of the presence of the t times exponential term. This time we consider the linear autonomous system dx by dt is equal to minus x plus 2y, and dy by dt is equal to minus 2x minus 1. A is equal to minus 1, B is equal to 2, C is equal to minus 2, and D is equal to minus 1. Plugging those in to the characteristic equation, we'll wind up r squared plus 2r plus 5 is equal to 0. This time, the roots are going to be complex. The real part of this real part is going to be negative, so actually that will lead to an asymptotically stable solution. I've already written down the solutions for x and y. It's e to the minus t times x naught cosine 2t plus y naught sine 2t. Y is equal to e to the minus t, y naught cosine 2t minus x naught sine 2t. Let's go ahead and take a look at what the trajectories look like in the neighborhood of the critical point 0, 0. When the roots of the characteristic equation are complex, the critical point will be a spiral point. For this particular system, the trajectories travel in a clockwise direction, approaching the critical point as t approaches infinity. Hence, this system is asymptotically stable. Then finally, we'll consider similar looking set of equations, similar linear autonomous system. dx by dt is equal to y, and dy by dt is equal to minus x. This basically is just a linearized simple pendulum problem. There you'd have a factor out in front, g over L. But if I plug in A, B, C, and D, here A is equal to 0, B is equal to 1, C is equal to minus 1, and D is equal to 0. characteristic equation in this case is just going to be r squared plus 1 is equal to 0. And the two roots there are equal to plus or minus I, which are purely imaginary. This system will lead to a center type critical point, and the solution will be stable. So let's go ahead and take a look at that. Trajectories plotted in the neighborhood of the critical point 0, 0. Finally, we consider a center type critical point. The roots of the characteristic equation are imaginary. This brings us back to the trajectory of a simple pendulum that has been linearized. Such systems are stable. The code that generated these plots was written in the Python programming language and made use of matplotlib. This Python script has functions that generate the trajectories in the neighborhood of several different kinds of critical points, including a proper node, an improper node, a saddle point, a spiral point, and a center. I'll use Thani, which comes installed with the Raspbian operating system on the Raspberry Pi computer, to edit and run the Python code. Of course, this code can be run on any system which has Python installed. The PyPlot module is imported from matplotlib, splot, and the exponential, square root, cosine, and sine functions are imported from the math module. Lines that begin with the hashtag are called comment lines. Anything else that follows the hashtag on a line is ignored by the Python interpreter. Comments are usually used to provide information about the code and are sometimes used to comment out lines of code that the programmer does not wish to be executed. The menu calc types function prints out a menu of choices. The proper node, improper node, saddle point, improper node A, spiral point, and center functions each generates a trajectory given a particular starting point for a particular linear autonomous system. The proper node function generates the x and y coordinates of the linear autonomous system described by dx by dt is equal to minus 2x and dy by dt is equal to minus 2y. The proper node function has the parameters a0, t0, h, and t max. a0 contains the starting x and y coordinates. In order to use this function, a list containing the starting x and y coordinates must be passed to the function when it is called. The parameters t0, h, and t max represent the starting time, the time step, and maximum time at which the trajectory is to be calculated. These three parameters have default values, which means that if the proper node function does not pass values for them, the default values of 0, 0.001, and 5 are used. The x and y lists, which contain the x and y coordinates for the trajectory, are returned by this function. The other 5 functions have a similar form to the proper node function. The choosefun function assigns to the variable a two-dimensional list which contains the coordinates of the starting points for the trajectories to be determined. An if-else statement is used to assign values depending on the user's choice. In addition, the appropriate function is assigned to the variable fun, and tm is assigned a value. The genplot function is the main function of this script. First, the menu calc types function is called, and the user is prompted to enter a choice. Then the choosefun function is called with the user's choice passed as the argument. The choosefun function returns a list of starting points for the trajectories, of reference to the function that generates the trajectories, and the maximum time. The subplot function creates a subplot, and colors is assigned a list of names of colors that are defined in matplotlib. Each iteration of the for loop, the function that generates the trajectory corresponding to a particular starting point is called, and a scatter plot is created. We'll run the code. You can save the plot by clicking on the save icon. This code is available on the BocaPhysics website. Now, a stable solution is a solution that starts sufficiently close to the critical point and stays in the neighborhood of the critical point as t goes to infinity. An example of that was the linearized simple pendulum problem, in which case the trajectory was an ellipse. There are also asymptotically stable solutions. In that case, the solution not only stays in the neighborhood of the critical point, but it approaches it as t goes to infinity. We also looked at unstable solutions as well. An example of that was the saddle point. Now, the linear autonomous system, again, is dx by dt is equal to ax plus by, dy by dt is equal to cx plus dy. We determined, or predicted rather, the stability based on the roots of the characteristic equation. Characteristic equation being r squared minus a plus d times r plus AD minus BC is equal to 0 with the added condition AD minus BC is not equal to 0. Well, basically, there's a theorem that enables you to determine the stability of the critical point based on the roots of the characteristic equation. I'm not going to prove that. It's far more useful to summarize the results in a table. So let's take a look at that now. Summarized in this table are the roots of the characteristic equation, the type of critical point, and whether the critical point is asymptotically stable, stable, or unstable. If the roots are positive, equal, and real, then the critical point is either a proper node or an improper node, and it's unstable. If the roots are negative, equal, and real, then the critical point will still be either a proper node or an improper node. However, this system will be asymptotically stable. If the roots are real, positive, and different, the critical point will be an improper node and will be unstable. If the roots are negative, real, and different, the critical point will be an improper node, but asymptotically stable. If both roots are real, but one root is positive and one root is negative, then the critical point will be a saddle point, which is always unstable. If both roots are complex, with the real part positive, then the critical point will be a spiral point and unstable. If the real part is negative, then the spiral point will be asymptotically stable. If both roots are purely imaginary, one positive and one negative, then the critical point will be a stable center. Now I'm going to extend these results to nonlinear differential equations, in particular nearly linear systems. So what do I mean by that? Well, first of all, we need to add an extra term here. These are the nonlinear terms. And they too both depend in general on x and y. What do I mean by the term nearly linear? Well, let's make the substitution that x can be written as r cosine of some angle, and y likewise can be written as r sine of some angle. So in order for a system to be nearly linear, must be the case that the limit as this r goes to 0 of the nonlinear term divided by r also has to go to 0. And a similar expression for g as well must also hold. So what might that be? Well, terms of the form x squared, y squared, xy, and so forth. There's a theorem that tells you that the information about the stability of the critical point of a nearly linear system can be obtained from the corresponding linear system. So what do I mean by that in particular? Well, recall, we just looked at this linear autonomous system. Dx by dt minus 2 is equal to minus 2x, and dy by dt is equal to minus 2y. We looked at the characteristic equation. We also plotted it out. The critical point there, located at 0, 0, is asymptotically stable, and it was also a proper node. Now, a nearly nonlinear system, or rather a nearly linear system, could be minus 2x plus xy. It could be anything in that form, but we'll just take this example in particular. Now, if I were to make the substitution that x is equal to this r cosine theta, y is equal to r sine theta, and divide that by r and take the limit as r goes to 0, that contribution is going to go to 0. So it is nearly linear. Therefore, if I know what the stability of the critical point of the linear system is, I can say what the stability of its nonlinear counterpart, or nearly linear counterpart, is going to be. So rather than prove this, it's more useful to summarize that in a table. Highlighted in red are the types of critical points that can also arise in almost linear autonomous systems. For cases where the roots are equal and real, spiral points are also possible. When the roots are purely imaginary, the trajectory could be either a center or a spiral point, and the stability is indeterminate. In order to investigate the properties of almost linear autonomous systems, I've written code that implements the Runge-Kutta method. This code has also been posted on the BocaPhysics website. This Python script implements the Runge-Kutta method in order to solve linear and almost linear autonomous systems. The pyplot module is imported from matplotlib, and the square root function is imported from the math module. The menu calc types function prints out options to the user. This time the user has the option of solving almost linear autonomous systems in addition to linear ones. The choose_fg function assigns lambdas to the variables f and g. The expressions are assigned according to the user's choice. The enter starting values function prompts the user to enter pairs of starting points for the trajectories. The user enters anything that can't be converted to a floating point, or doesn't enter two numbers when prompted to enter a pair of numbers. Default values are used. The choose_starting_values function assigns a two-dimensional list of values to the variable a, depending on the autonomous system the user chooses. If the user wants to enter custom values, in which case data choice would not be equal to y, then the enter starting values function is called. The RK function implements the Runge-Kutta method. This function is defined to have the parameters f, g, a0, t0, h, and t max, which represent the two lambdas created in the choose_fg function, the starting point of the trajectory, the initial time, the time step, and the maximum time. The genplot function calls the menu calc types function and prompts the user to choose the autonomous system to be solved. Next, the choose_fg function is called. If the user does not enter a valid choice, the genplot function is exited and the script ends. If the user does enter a valid choice, the user is asked if stored starting values should be used. The choose_starting_values function is called and the return list and float are assigned to a and tm respectively. Next, the subplot function is called and returns axes for the subplot, and colors contains a list of colors recognized by matplotlib. Each iteration of the for loop, the RK function, which generates a trajectory corresponding to a particular starting point, is called, and a scatter plot is created. Now we'll run the script. We'll enter 7 to solve the system dx by dt is equal to minus 2x and dy by dt is equal to x minus 2y. For comparison, we'll open the plot that was generated from the exact solution. Next, we'll enter 8 to solve the linear system with the nonlinear term y squared added to the dx by dt equation. Finally, this script allows the user to enter new starting points. We'll select option 2 this time, and we'll enter no for the stored starting values. This code is available on the BocaPhysics website. Now we return to the simple pendulum problem. You can understand now what stability means in this particular system. If the pendulum is perturbed from its equilibrium point, which would be hanging straight down, what happens? Well, we've assumed that there's no damping on the system, so the pendulum is just going to swing back and forth. It will remain in the neighborhood of its equilibrium. We want to look, however, now at the non-linearized system, minus g over L times sine of x. And I need to show that I can apply the previous analysis to this particular system. So I'm going to rewrite the right-hand side of the equation. So we have minus g over L times x minus g over L sine x minus x. So basically all I've done is to add minus g over L times x plus g over L times x to the system. Okay, so now we've written in the form, I've got the linear term, and that linear system we've already solved, and now we've got a nonlinear term as well. I need to show that if I take the limit as r goes to 0, this term sine x minus x over r, that is going to go to 0. If I expand sine x out, then we'll get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Well, those x's will cancel out, and you'll be left with the term of basically x cubed over 3 factorial over 1 over r. Now, if you make that substitution, you'll have something like r cosine v cubed over r and 3 factorial. Taking the limit as r goes to 0 here, clearly this term goes to 0. So I can use information about the linear system to figure out what's going to go with this nearly linear system. Okay? So this is nearly linear. Let's sketch out the phase plane here. We've got a critical point at x equals 0, y equals 0. We already did the analysis there because in that case, the roots of the characteristic equation of the linear system were purely imaginary. So what that tells you is that that critical point is a stable center. But you've also got critical points all along the x-axis. This is it. X equals pi, x equals 2 pi, x equals 3 pi, minus pi, minus 2 pi, minus 3 pi, and so on. So how do we investigate what kind of critical points those are? How do you do that? We're going to make change of variables. Let's say we want to investigate the point x equals 2 pi and y equals 0. So we'll set x equals to 2 pi plus u. I'll just wind up with du by dt is equal to y. dy by dt is equal to minus g over L times sine 2 pi plus u. But that's just equal to sine of u. This has the same form as our linear autonomous system, but of course with the change of variables. So what that means is that for all the points, 2 pi, 4 pi, and so forth, those are also all going to be stable centers. So you're going to have basically elliptical trajectories centered about x equals 0, x equals 2 pi, x equals minus 2 pi, and so forth. What about the points pi, 3 pi, minus pi, and minus 3 pi? So let's make a change of variables this time. We'll just look at one in particular. What is this going to be? So instead of setting x equal to 2 pi plus u, we'll do x is equal to pi plus u. So now when I substitute in or calculate sine of pi plus u, that's not equal to sine u, that's equal to minus sine u. And now the equations have a different form. It's going to be g over L times sine of u and du by dt, and before is just going to be equal to y. So now there's a difference here. Before we had a minus sign, now this is positive. So I need to figure out what kind of critical point does its linear counterpart have. So in other words, we look at du by dt is equal to y, and dy by dt is equal to g over L times u. And I write down the characteristic equation for this system. In this case, a is equal to 0, b is equal to 1, c is equal to g over L, and d is equal to 0. Now in this case, characteristic equation is just going to be r squared minus g over L is equal to 0. I solve for that. It's plus or minus square root of g over L. Now, what system, what kind of critical point is this system going to be? Well, look back to the linear system. That, in fact, is going to be a saddle point. So what you'll see is some trajectories that are going to approach the saddle point and others that are going to go away from it. Let's go ahead and look at a more complete picture of what happens in the phase plane. For comparison, we'll look at the trajectories of the linearized simple pendulum problem. In each case, trajectory forms a closed loop, and each loop is traversed in a clockwise direction. In contrast, this is the phase plane of a simple pendulum, which is almost a linear problem. Notice the 6 closed trajectories, 2 centered at x equals 0, 2 at x equals 2 pi, and 2 at x equals minus 2 pi. These 3 critical points are stable centers. Notice the 4 critical points at x equals minus 3 pi, minus pi, pi, and 3 pi. These are all unstable saddle points. Several trajectories have been shown, some which approach the critical point, and others that depart from it. Above and below the trajectories that approach and depart from the saddle points are trajectories that appear sinusoidal. The trajectories that approach and depart from the saddle points separate the phase plane into different sectors. This is why such a trajectory is called a separatrix. Finally, we'll look at the damp pendulum problem. And the motion of a damp pendulum is governed by the equation ml squared times second derivative of theta with respect to time plus c times L times derivative of theta with respect to time plus mgl sine theta is equal to 0. M represents mass, L is the length of the pendulum as before, c is the damping coefficient, and g, of course, is the acceleration due to gravity. In order to solve the system, we're going to convert this second order differential equation to 2 first order differential equations, make the substitution as before that x is equal to theta and y is equal to d theta by dt. That leads to the autonomous system dx by dt is equal to y and dy by dt is equal to minus g over L times sine x minus c over ml times y. Now, in order to investigate the critical points of this system, we have to linearize it. Which means essentially I replace sine x by x, and in this case, a is equal to 0, b is equal to 1, c is equal to minus g over L, and d is equal to minus c over ml. If I plug those in to my characteristic equation and solve for roots, I'll find that that's equal to minus c over ml plus or minus the square root of c over ml squared minus 4g over L all over 2. Now, there are three cases here. Depending on the relative values of the damping coefficient c, the mass m, and the length of the pendulum. First possibility is that this value of the radical sign is just equal to 0. Well, if this is just equal to 0, then the roots are going to be equal to minus c over 2 ml. They're both going to be real, they're both negative, and they're equal to each other. The type of critical point that is for the linear system is going to be asymptotically stable. No. For the almost linear version, which is the one we're interested in, other words, when you've got sine x here, the critical point will either be an asymptotic stable node or a spiral point. Another possibility is what if this value is positive, and that means this second term will be a positive real number, in which case the roots, when you add that to minus c over ml, are going to be real, unequal this time, and they're both going to be negative. And for both the linear and nearly linear systems, that is going to be an asymptotically stable node. Last case is if this is negative, in which case this second term will be imaginary. So we get a complex number, complex roots. The real part is going to be negative. The only possibility there for both linear and nearly linear systems is asymptotically stable spiral point. Now I'm going to look at case C in more detail. So, in the neighborhood of the critical point at x equals 0, y equals 0, the trajectory is an asymptotically stable spiral point. But x equals 0, y equals 0 is not the only critical point. In fact, there's a series of critical points that lie along the x-axis. Critical points at x equals pi, 2 pi, minus 2 pi, and so forth. In order to determine the critical point at 2 pi and its stability, I'm going to make a change of variables. We'll assume that x is equal to u plus 2 pi, and therefore, the autonomous system in the new coordinates becomes du by dt is equal to y, and dy by dt is equal to minus g over L sine u plus 2 pi minus cm, cy over nl. Now sine of u plus 2 pi is just equal to sine of u. So basically, the form of this system is exactly the same as what we started with. It's just in different variables. So therefore, the critical point at even multiples of pi is going to be asymptotically stable, and it's going to be a spiral as well. Now, what about the points pi minus pi, odd multiples of pi? Well, instead, we're going to make the substitution that x is equal to u plus pi. And when I do that, sine of u plus pi is in fact equal to minus sine of u. So now there is going to be a difference. So now my linear autonomous system, or rather my autonomous system, is going to be du by dt is equal to y, and dy by dt is equal to g over L sine u minus c over ml y. So I'll need to linearize this equation, and that'll be positive g over L u. When I write down the roots of the characteristic equation, instead of this being a minus sign, it's actually going to now be a plus sign. So what effect is that going to have? Well, this term, the second term, is going to be positive, and it's going to be a real number. So therefore, the roots are going to be real. They're going to be unequal. One's going to be positive, and one's going to be negative. Points at odd multiples of pi are therefore going to be saddle points. So let's go ahead and take a look at the plot to see a more complete picture of the phase plane of a damped pendulum. Here we consider the phase plane of a damped pendulum. The critical points at x equals minus 2 pi, 0, and 2 pi are asymptotically stable spiral points. Damping is a reason for the spiral points instead of centers. As with the undamped simple pendulum, the critical points at x equals minus pi and pi are unstable saddle points. Once again, a trajectory that approaches or departs from a saddle point and that separates the phase plane into sectors is a separatrix. The Python scripts described in this video lecture are available at www.BocaPhysics.com. To learn more about the textbook Learning IoT with Python and Raspberry Pi, go to www.learningiot.net.